Today's daily LeetCode problem of the day is height of a binary tree after subtree removal. Queries number 2458. For this problem, we're given the root of a binary tree with an n amount of nodes. Each node is assigned a unique value from 1 to n. We're also given an array queries of size m. So we have to perform an m amount of independent queries on the tree, where the ith query we do the following. We remove the subtree rooted at the node with the value queries of I from the tree. It is guaranteed that queries of I will not be equal to the value of the root. So we want to return the array of size, an answer array of size m, where answer of I is the height of the tree after performing the ith query. So queries are independent, so the tree returns it to its initial state after each query. And the height of a tree is the number of edges in a long simple path from the root to the sum node in the tree. So in example 1, the longest possible subtree currently is 1, 4, 5, 7. After we remove index 4, the longest possible subtree is 1, 3, 2. If we did have another index in queries, so this is index 0, if we had index 1, for example, the node 4 would return. Basically, the tree would return to its original form, so we could do the next query. So, for this problem, we want to determine the maximum height of the remaining tree after removing a subtree for each query. So if we look at example 2, our queries is of length 4, so our output is also of length 4, where we calculate the deepest it can go based off of each index change. So how are we going to approach this? We are going to traverse the tree twice to collect its height information, once to the left, once to the right. Then we will use this to account for the different scenarios where a node and its subtree are considered imaginarily removed or temporarily removed. We want to then process the queries by simply looking them up in our pre-computed heights in the array. So let's just dive right into the code. First thing we're going to do is we're going to initiate two variables, our max height after removal and our current height. So we're going to have a static final, meaning we do not want this to change. It's going to be an integer array of called max height after removal. And this is going to be a new integer array, and we're going to set it to the absolute maximum possible height. So this is going to be 100,001. And this is going to be the absolute maximum height based off of whatever changes we make, and that's going to be the default setting. We're also going to have an index current max height, and we're going to make it global. That way we can update it in any function. So again, we're going to set max height after removal to 100,001 to handle the constraints of the problem where the number of nodes can be up to 100,000. We're now going to look at our main method. So we're going to process the input and return our query results. So we're going to first traverse to the left, calculate our max height, and then we're going to traverse from right to left. So left to right, calculate our height, and then right to left. So traverse left to right. We're going to pass it our root and index 0, or height 0, and then we're going to pass or update our current max height to 0, and then we're going to traverse right to left, root and 0. So we're first going to traverse the tree from left to right, and then we're going to reset our height for the second traversal, where we're going to go from right to left. And this is just going to help us gain all the information we need based off of the tree's heights to make calculations when we remove a node. So we're now going to have our, we're going to initiate a couple variables. First is going to be our query count, which is just going to be the length of query. So queries.length. And then we're going to have an integer array results, which is just going to be our results array, which is going to be a new integer array of query count length. Now we're going to have a for loop, so for int I is equal to 0 as long as I is less than our query count. I can increment, and we're going to update our our results based on our max height after removal of queries of I. So we're going to have to update our result index, so results of I, based off of this array and what happens in queries of I, or whatever index is in queries of I, and then we're going to be able to return our results. So we're going to traverse the tree twice. We're going to reset our height after our first traversal so it starts fresh. And then we're going to process each of our queries in order and simply look up our pre-computed heights from each index and store it in our query results. So let's go ahead and build these functions. So we're going to have our private, it's going to return nothing, so void traverse left to right. It's going to receive a tree node. It's going to receive an integer current height, and it's going to be recursive. So our base case is if we reach a null node or a non-existent node, we're going to return. So if node is equal to null, return. As simple as that. Now we're going to store the maximum height if this node were removed. We're going to update the current maximum height, and then we're going to traverse left subtree first, then right subtree. So let's update our max height. So max height after removal of node dot value is going to be equal to our current max height. So we're updating this array up here, our global array. We're updating it so that at node's value we have its maximum height, if this node were removed, stored in the array. We're then going to update our current max height. So current max height is going to be equal to math.max of current max height and current height. And then we are going to further traverse the tree. So we're going to traverse left to right 2 times, but with the left node and the right node of our current node. So traverse left to right of node dot left and current height plus 1. Traverse left to right of node dot right of and current height plus 1. So that is our traverse from left to right. Our traverse from right to left is going to be the exact same thing, but from the right to the left. So private void traverse right to left. It's going to receive a tree node. It's going to receive an integer current height if node is equal to null, return. We're going to update our maximum height if this node were removed, so max height after removal of node dot value is going to be equal to math.max. This is going to be math.max of, we're going to take in consideration what this value was. So it's going to be math.max of our max height after removal of node dot value. So we're going to take into consideration what the previously identified max height was and the current max height. So current max height. So if for some reason this traversal found this node deeper, then it will update that value. Otherwise, it'll stay the same. Then we're going to update our current max height. So current max height is equal to math.max of our current height and our current max height. And then again, we're going to traverse right to left using both the right node and the left node. So traverse right to left of node dot right and current height +1, and traverse right to left of node dot left of current height +1. Cool. So this works the exact same as the last one, except we're going to update our max height for each node by taking the maximum between the existing height we previously calculated and the current height. And that's that. So this one's going to search the right subtrees first, and then the left subtrees. This one searches the left subtrees first, and then the right ones. Cool. So let's go ahead and run this real quick. So this passes our test cases, and it'll pass all solutions. Boom. So that's it. Thank you for watching, and follow for more daily LeetCode solutions. If you want to stay, I'm going to walk through an example real quick, but thank you for watching the solution. So let's go through an example real quick to see how it works. So if we imagine that we have this tree, 1, 3, 2, 1, 4, 6, 1, 4, 5, 7. If we receive a query to remove the subtree at 3, so our new tree is going to look like this: 1, 4, 6, 1, 4, 5, 7. The height of the subtree is still 1, 2, 3, and basically we're going to keep this information stored. So starting at node 3, the deepest possible subtree we could get is 2, or 1. Including 3, it would be length 2. So 1, 2. So we're going to keep that information stored at our max height after removal by imagining that we already removed 3. So if 3 wasn't there, the max height we could get after removal from node 1 would be 1, 2, 3. But if we removed 4, let's say, the max height we could get from node 1 is now 1, 2. So we're going to keep all this information stored in our max height after removal by keeping how deep each node goes in their assigned spot. So 4 to the left is only 1, 4 to the right is 2. So if we get rid of 4, the deepest possible is no longer this 3, it's just the 2 on the left. We're also going to make sure that we don't delete any nodes. That's why we're just keeping track of their positions and how deep they go. Because after we remove 8, for example, and the next query is 3, 8 comes back. So this is still a possible subtree in our next query. It doesn't disappear. So in our traverse left to right, we look at our left subtrees first. So say we're at 5. We're going to look at 8, and then 2, and then 4, and then back up to 2, and then 6, so on and so forth. So we're going to go left to right. In our right to left, we're going to look at 9, then 7, and then 3, and then 8, and then 1, and then 2, and then 6, and then 4. So that's it. Thank you, and follow for more daily LeetCode solutions.